Have you ever stopped and wondered how your refrigerator actually makes things cold? I mean, it feels like magic, right? Well, it's all about this fascinating engineering cycle. And in this explainer, we're going to pull back the curtain and demystify that cycle step by step. Let's dive right in.
So that's really the big question we're tackling today. We're going to go on a little quest, you and me. We're going to follow this invisible substance, the refrigerant, as it travels through a system. And in the process, we are going to crack the code of its incredible cooling power.
And here's our game plan. First, we'll get the mission briefing. Then, we'll meet the key players in the system. After that, we'll learn how to read an engineer's secret map, trace the refrigerant's path, do some pretty simple math, and finally, give the system a performance score. Sound good? Let's go.
All right, so every good engineering problem starts with a really clear objective. So let's take a look at our mission briefing.
Okay, here's the deal. Our task is to analyze a refrigeration cycle that needs to deliver 50 kilowatts of cooling. That's a decent amount of power. We're told it uses a specific refrigerant called R22, and we have two critical temperatures. It dumps its heat at 35 degrees Celsius, and it absorbs heat at a very chilly minus 15 degrees Celsius. These two numbers are our anchors for this entire problem.
So, to really understand this journey, we first need to meet the team. I want you to think of this refrigeration cycle as having 4 heroes, each one with a super important job to do.
First up is the compressor. This thing is the powerhouse, the engine of the whole system. Its job is to suck in the refrigerant when it's just a cool, low-pressure gas, and then squeeze it hard. This compression dramatically jacks up both its pressure and its temperature. It really gets the whole process moving.
Next, that hot, high-pressure gas flows right into the condenser. The condenser's role is basically to be the heat dispatcher. It lets all that heat escape to the outside air, which causes the refrigerant to cool way down and, you guessed it, condense from a gas back into a high-pressure liquid.
So now we've got this high-pressure liquid, which brings us to the expansion valve. This little device is a total game changer. It acts like a gatekeeper, creating a sudden, massive drop in pressure. This super-fast expansion makes the liquid refrigerant intensely cold, getting it primed and ready for its main mission.
And that mission happens right here, in the evaporator, our cooling champion. This is where the real magic happens. The super cold refrigerant flows through coils and absorbs heat from the space we want to cool, like the inside of your fridge. All that heat it soaks up makes it boil, turning it back into a low-pressure gas. And just like that, the cycle is ready to start all over again.
So we have these 4 components, and each one is causing changes in pressure, temperature, and even the state of the refrigerant, from gas to liquid and back again. But how on earth do you track all of that? Well, we need a map, and for engineers, that map is called the pH chart.
Now, I know, this chart can look pretty intimidating at first, but don't worry. Just think of it like a treasure map. The vertical axis is pressure, and the horizontal one is something called enthalpy, which is really just a fancy word for the total energy in the system. Every single point on this map tells us exactly what our refrigerant is doing. It's awesome.
Okay, it's time to put all the pieces together. Let's take our 4 hero components and plot their journey on this treasure map.
The process is actually pretty straightforward. First, we'll find the 4 key points on the chart that represent what the refrigerant looks like as it leaves each component. Then, we'll just connect the dots to see the whole cycle. And finally, we'll read off the treasure, that enthalpy value, at each of our 4 points.
Okay, let's trace the path. Point 1 is where the refrigerant is about to enter the compressor. It's what we call a saturated vapor, and it's at minus 15 degrees. From point 1 to point 2, the compressor does its work, turning it into a hot, superheated vapor. Then, from 2 to 3, the condenser cools it down until it becomes a saturated liquid at 35 degrees. Finally, from 3 to 4, the expansion valve does its thing, dropping the pressure and turning into a super cold mix of liquid and vapor ready to absorb heat all over again. So by finding these 4 points on the actual R22 chart, we can just read their energy values right off the x-axis. We find that point 1 is at 400. After the compressor, point 2 is at 440. After the condenser, point 3 is at 240. And here's a neat trick. The process through the expansion valve is so fast, it doesn't change the total energy. So point 4 has the same value as point 3, 240. These 4 numbers are the keys to the entire kingdom. We've read the map, we've found our treasure values. Now, for the payoff. It's time to use these numbers to see how well our system is actually performing. First up, let's calculate the refrigeration effect. This sounds technical, but it's really just the amount of heat absorbed in the evaporator. In other words, it's the useful cooling we get. The formula is super simple. It's just the energy at the end of that process, H1, minus the energy at the beginning, H4.
And that gives us 160 kilojoules per kilogram. So what does this actually mean? It means for every single kilogram of R22 that goes around this loop, our system produces 160 kilojoules of pure cooling. That's our output.
Okay, but cooling isn't free, right? What's the cost? Well, that's the work done by the compressor. To find the total power, we first need to know how much refrigerant is flowing. Since we need 50 kilowatts of cooling total, and we know each kilogram gives us 160 kilojoules, a quick division tells us we need to pump about 0.3125 kilograms every second. We just multiply that flow rate by the energy the compressor adds, which is H2 minus H1.
When we plug in the numbers, we find the compressor needs 12.5 kilowatts of power to run. This is the electrical energy we have to pay for. This is our input.
Finally, let's get the overall efficiency score. This is called the coefficient of performance, or COP for short, and it's just a simple ratio of what we get to what we put in. It's our benefit, the refrigeration effect, divided by our cost, the compressor work.
Dividing 160 by 40 gives us a COP of exactly 4.0. Now, this number doesn't have any units, but it's incredibly useful. It tells us that for every 1 kilowatt of electrical power we feed into that compressor, we are successfully moving 4 kilowatts of heat energy out of our cold space. That's a fantastic return on our energy investment.
So let's put it all together and take one last look at the final performance report card for our system.
And there they are, the final results. We get 160 kilojoules of cooling for every kilogram of refrigerant that flows. It costs us 12.5 kilowatts of power to drive the whole thing. And that gives us a really solid overall efficiency score, our COP of 4.0. Mission accomplished.
So we cracked the code. But this is really just the beginning. Now that you understand how to map this journey and how to measure the performance, I've got a final thought for you. Looking at our map and the formulas we used, what single change to the system do you think would have the biggest impact on improving that COP? Ponder that one for a bit. Thanks for coming along on the journey.